Okay, so for this, I'm going to step through these about 9 problems through a couple videos. So the first one we're going to start off with is number 3 for these optimizing problems. So the first one here, we've got a wire length of 12 meters divided into 2 pieces. They are bent into a square and a circle. How should this be done so you want to minimize their areas? So we have our length of 12. We break it up into 2 parts, x and 12 minus x. Now what I'm going to do is I'm going to say that this x represents the perimeter of the circle, or the circumference of a circle. The circumference of a circle is equal to 2 pi r. So it would be x is equal to 2 pi r, which means r is equal to x over 2 pi. Now for the square, the perimeter of a square is 4l. Okay, which means that L is equal to 3 minus x over 4. Okay, that's just solving. So now these can be plugged into their area formulas. The area of a square is L squared, which would be 3 minus x over 4, that whole thing squared. And then the area of a circle is pi r squared. So we'll plug in what we got for r and then square it. So that means that we have approximately x squared all over 4 pi is equal to area of the circle. And the area of the square, we're going to keep it as this 3 minus x over 4 squared, just because it's going to be a little easier for us to do the derivative of that. Now it wants to know what the sum of the area. We want to minimize the sum of the areas. So what we do is that we add these together, take the derivative, find the min. And so the sum of the areas, x squared all over 4 pi plus 3 minus x over 4 squared is equal to the area. We're going to want to take the derivative of it. So the derivative of this would be x over 2 pi plus it's going to be minus 1/2 3 minus x over 4. And that's just taking the derivative with the chain rule. You drop the 2 and then you multiply it by the derivative of the inside, which is a negative 1/4, which gets you the negative 1/2 out front. And now we're going to minimize this, so we're going to try to get it so it's equal to 0. X over 2 pi, I'm going to distribute this negative 1/2. So it'd be negative 3 over 2 plus x over 8. Move the 3 over 2 to the other side. 3 over 2 is equal to 8x plus 2 pi all over 16 pi. Cross multiply everything. 48 pi is equal to 16x plus 4 pi. Again, that's still me solving this through, solving for 0. And 4 pi x, which gets us an x is equal to 48 pi all over 16 plus 4 pi, which reduces down to x equals 12 pi all over x plus pi. And so now what you would do is that you would check, you would plug this into the original area formula, which is right there. You'd plug it into there. You'd also plug in a 0 and a 12, because those are your endpoints. Your endpoints were 0 and 12, so you'd plug those two numbers in, and then you'd plug in what we found as our critical point of this problem and see where do we minimize it. And when we do this, we find out that when we plug in a 0, we end up getting about 9. When we plug in a 12, we get about 11.5. And when we plug this one in, we end up getting 5.04 approximately meters squared. So that is our minimum area, and that is our x length for our minimum area. Okay, so, or the circumference of the circle. And then the square would be everything left over, which again, this is about 5.28. Okay, so that was number 3. All right, number 5 is dealing with a flexible tube in an L shape. Well, an L shape has 90 degrees, which means we're going to be using Pythagorean theorem and the distance formula. And it's 4 meters in length. So that means one One side is x, the other one is 4 minus x. So now we're going to throw this into the distance formula, which I'll say is h of x, whatever the length is equal to the square root of x squared plus 4 minus x, that whole thing squared. Okay. And we'll take the derivative of this, which the main thing here is with this square root, we're going to get our zero or critical points inside the square root. And so we're trying to zero out when we do our derivatives and everything. So when we take, if we're just looking on the inside, okay, if we want to simplify it, we end up getting minus 8x plus x squared. Added together gets you 2x squared plus 16 minus 8x. And we're taking the square root of that. Well, since we want to zero it out, we can just take the derivative of the inside, because the stuff on the outside it's not going to really do anything. The square root won't really matter. And so we'll end up getting a 4x minus 8. Okay, with the derivative of the inside, or where we zero out the inside, which is what we're looking for. And so we set that equal to 0, and we end up getting x is equal to 2. So that means that one of the sides has to be 2, which means the other side also has to be 2. Now when we check this with our distance formula, we find out that that gets us about 8 as our distance in between, okay, or the square root of 8. And so that is our minimum distance, is when x is 2. So one length is 2 and the other length is 2, basically giving us a square. Okay. Now again, all you do is once you set up your formula, you find the derivative of it and set it equal to 0. Alright, so now this one with the rancher, where he has his cattle in a corral that looks like this. Okay. What we're going to do is that I'm going to label one side as y and the other side as 2x. And the reason for that is because I want to try to avoid the fraction in for the radius. Okay. So the maximum amount of fencing that he has to corral all this is 600. So 600 is equal to the perimeter, which would be 2x plus 2y, because we've got 2 y's, plus the circumference of the semicircle that is on the top. And so the circumference of a circle is 2 pi r, or in this case it'd be 2 pi x. Half of that would just be pi x. So pi x would be that. Now what we're going to do is we're going to solve for y. It's going to be the easier one to solve. And that gets us 600 minus 2x minus pi x all over 2 is equal to y. Okay. So now with our area formula, the area which we're trying to maximize, what we're going to do is that we do the area of the square, or the rectangle, which would be 2xy, add it to the area of the semicircle, which would be pi r squared all over 2. And r is x in this case. And now we're going to take this y and plug it in here. Well, since we have this 2 and this 2, or this 2 out front is being multiplied by something over 2, they kind of disappear, leaving us with just x parentheses 600 minus 2x minus pi x plus pi x squared all over 2. Distribute 600x minus 2x squared minus pi x squared plus pi x squared all over 2. Okay. Now we can either combine things now or take the derivative. I'm going to take the derivative right now. So the derivative, a prime, would be 600 minus 4x minus 2 pi x plus pi x. Combine like terms, simplify it down. We're going to have 0 is equal to 600 minus 4x minus pi x. Okay, that's from combining these two. moving these onto the other side, giving us a 4x plus pi x is equal to 600, which means that x is equal to 600 all over 4 plus pi. Okay, so that's x. And now what we'll do is that we'll take this, plug it in here, to find our bottom length. And so our bottom length would be double that, which would be, so one dimension that we know, which this will optimize it, this one will be the maximum. One dimension will be 1200 all over 4 plus pi. Okay. And now we've got to find the other dimension. So what we're going to do is we're going to take this and plug it in for the x's in this equation to find what y would have to be. So we'll have 600 minus 1200 over 4 plus pi minus 600 pi all over 4 plus pi all over 2. Get a common denominator, getting us 2400 plus 600 pi minus 1200 minus 600 pi, and that's all over 4 plus pi. Combining like terms, getting us about 1200, just 1200, because the 600s cancel, all over 4 plus pi, all over 2, all over 2. Reducing that means our y would be about 600 all over 4 plus pi. So our two dimensions would be 1200 over 4 plus y and 600 over 4 plus y, which come out to be approximately 1.86 and or 168 point something and double that, so 200 and something. So this would be our dimensions. I know the one in the back of the book will probably give you a different number, or a different fraction, but if you were to plug this into your calculator, you see that the decimals come up as the exact same as what it is in the book. We just went a different route with the 2x, so we didn't have to deal with a 1x over 2 as our radius. We just kept it as x, which I believe makes it simpler.